This PowerPoint presentation is from section 15.1 of our textbook and covers the common ion effect, the effect of pH on solubility, and qualitative analysis. The presence of a common ion reduces the solubility of a sparingly soluble salt by Le Chatelier's principle. If we look at the solubility reaction of calcium fluoride with a KSP value of 4 times 10 to the minus 11, what happens if we add fluoride ion? We call fluoride a common ion for this system because it is shared. In other words, it's one of the ions already present in the system. If we add fluoride to the system, we know from Le Chatelier's principle that adding a product species should shift the system back towards reactants. This means that adding fluoride to a system in equilibrium, one in which there's already some solid calcium fluoride present, should result in additional solid being formed. Let's compare the solubility of calcium fluoride in water to the solubility of calcium fluoride in a solution that contains some fluoride ions already. First, we'll look at the solubility in water. To find the solubility of calcium fluoride in water, we set up an ice table as we have in the past. Calcium fluoride solid will dissociate into calcium ions and fluoride ions. We assume initial concentrations of the calcium and the fluoride to be 0. The reaction will proceed in a forward direction to produce some ions. We'll use S to represent the extent of reaction. Plugging in our equilibrium expressions to the KSP value, we get S times 2S squared should be equal to 4 times 10 to the minus 11, the KSP value for calcium fluoride. Combining terms and then solving for S gives us the solubility of calcium fluoride to be 2.15 times 10 to the minus 4 molar. What about the solubility in a solution that already contains some fluoride ions? Again, we can write the dissociation reaction and an ice table. In this case, though, instead of starting with just pure water, we're starting with a solution that's 0.1 molar in fluoride ions. So in the initial row for our ice table, we'll put in 0.1 for the concentration of fluoride ions. Otherwise, it's very similar. The reaction will proceed in the forward direction to produce some calcium ions and add to the fluoride concentration. We can put in our equilibrium expressions into the KSP term. So S times 0.1 plus 2S squared will be equal to the KSP value of 4 times 10 to the minus 11. And when we solve this expression for S, we get 4 times 10 to the minus 9 molar. Compare these two numbers. Notice that the solubility of the calcium fluoride solid decreases in the presence of a common ion, in this case fluoride. This is a general result that is predicted by Le Chatelier's principle. This result is the common ion effect. The common ion effect states that when you have a common ion or shared ion already present, the solubility of the solid will be reduced. Notice, however, that the value of KSP did not change. What changed was the amount of calcium fluoride that would dissolve. Another parameter that can affect the solubility of a salt is pH. You probably already have some practical experience with this idea. You may know that you can use vinegar to clean out the calcium deposits left inside a tea kettle or coffee pot. Why does this work? It works because the calcium deposits are typically calcium carbonate solids. These solids are more soluble in acidic solutions, and so can be removed by using vinegar, which is an acid. Are all salts more soluble in acidic solution? No, only salts that have anions that are bases will be more soluble in acidic solutions. This is because the H+ from the acid will react with the basic anion, thus removing a product from the dissociation reaction. And by Le Chatelier's principle, this will shift the reaction to create more products. For example, calcium carbonate dissociates into calcium ions and carbonate ions. If we add acid to this system, the acid will react with the basic carbonate ions, causing their concentration to go down. When you remove a product from a reaction at equilibrium, you will drive it more towards products. Similarly, calcium hydroxide dissociates into calcium ions and hydroxide ions. Again, because hydroxide is a basic ion, addition of acid will cause that species to decrease in concentration, driving the reaction forward and dissolving more of the calcium hydroxide solid. There are some solids that will be more soluble in basic solution. Metal hydroxides that form complex ions with hydroxide will be more soluble in very basic solutions. The reason for this is the formation of a complex ion. For example, aluminum hydroxide solid, when it dissolves, would form some aluminum ions and hydroxide ions. If we add additional hydroxide to the system, we can create this complex ion, thereby bringing more of the aluminum into solution. Let's apply this to some questions. Which of the following ionic compounds would be more soluble in acid solution than in water? The first question asks for barium sulfate. What we have to determine is whether any of the ions that result from the dissolution of barium sulfate can react with acid. Since sulfate is a basic ion, barium sulfate will be more soluble in acid than it would be in water. What about lead-2 chloride? Neither lead ions nor chloride ions will react with acid, so lead-2 chloride will not be more soluble in acid than water. Iron 3 hydroxide does have a basic ion, hydroxide, so again this would be one that would be more soluble in acid. As would calcium phosphate, because the phosphate ion is also basic. The last topic in this section is qualitative analysis. Qualitative analysis is the process of determining which chemical species are present in a system, but not necessarily how much is present. That would be quantitative analysis. For ionic species, selective precipitation reactions can be used to determine which ions are present in a sample. Complex chemical analysis schemes have been developed to determine the presence or absence of nearly all possible ions in a solution. Chemistry students used to take a whole lab course on this one topic and could spend weeks in the lab to determine the composition of a single unknown sample. Today, there are instruments that can do much of this quicker, but it's still instructive to understand the old-fashioned process. The basic idea is that you take a solution containing a mixture of ions. And add some reagent that will selectively precipitate only one of them, which you can then remove from the system by filtration. The formation of a precipitate would be a positive test for that particular ion. The process is repeated using different reagents to test for and remove additional ions. This slide shows a scheme for separating and identifying all of the ions in the top box. First, the ions are separated into groups based on their solubilities with different reagents. For example, if the original sample shows a precipitate when chloride is added, your original sample must have contained one or more of the following ions: silver, mercury 2, or lead 2. On the other hand, if no precipitate is formed when chloride is added, your sample did not contain any of these ions. The sample is treated with a variety of reagents to separate the ions into the groups shown. Once you have the group separated, you can take each precipitate and analyze it to determine which of the ions is present. For example, for this group, do you have silver, mercury, lead, or all three? This slide shows part of the process to selectively identify the presence or absence of silver from the mixed precipitate. Here is our original solution, the addition of chloride to form a precipitate. In this precipitate, you could possibly have silver, mercury, or lead. It turns out that the solubility of lead 2 chloride is very temperature dependent, so the lead can be redissolved by heating the sample. The remaining precipitate could then be treated with ammonia to solubilize the silver ions, leaving behind, if a precipitate is left behind, it would contain mercury. The solution, or supernatant, could be further tested by adding acid to reprecipitate the silver chloride. Again, if a precipitate forms at this point, your original sample must have had silver. If no precipitate is formed, then you did not have silver. This concludes our presentation on section 15.1. Now you know where you can find the answers to all your solubility problems. Of course, they'll be in the solutions manual.